SwayamPrabha. Digital India. Educated India.
Welcome to the second lecture of module 3. In this lecture, we shall discuss about the process stereolithography apparatus. So, this slide shows the content of today's lecture. We shall discuss about the stereolithography apparatus, which in short called as SLA. This was the first additive manufacturing process like I have already mentioned. So, our today's focus will be to discuss its different subsystems. And as there are around 4 to 5 subsystems of this machine which I have identified to discuss in detail, in this lecture we shall discuss the two subsystems. Those are the laser beam and laser curing mechanism. The laser curing mechanism will be further divided into three. First is single bead, multi-bead and multi-layer. So basically here we will learn how these photopolymers are getting cured when UV light falls into it. If you recall this slide, we have already discussed the classification of photopolymerization based liquid additive manufacturing processes, and based on the different subcomponents or the subsystems available, we classified the process like the different scanning systems, different type of shape of UV light, different types of shape of the liquid photopolymer which we are using, and then different build directions and different recoating systems. Based on that, the 3D systems SLA and 3D systems SLA based on Zephyr, those are going to be our today's target, utilizes the galvanometer, laser beam, liquid wet, build the part in plus Z direction. The only difference is one uses the method deep dipping, another uses the method top feeding for recoating the new layer onto the liquid wet. So let me eliminate all the other processes from this slide, and now you can see very clearly the different levels of subcomponents available in this system stereolithography apparatus. This particular video will give us some idea of how this process works. So these are the typical 3D systems SLA machine what you are seeing here, and this is the graphical user interface for the machine. Here one can put appropriate process parameters and then the machine can operate appropriately. Here what you can see, these moving blue dots are nothing but the laser beam. After scanning a layer, as you have seen, a recoater passes over and removes the excess material. The process repeats itself and builds the part completely. Then later on, the part comes out like you are seeing here now. And later on, we can remove the excess amount of material which is provided here as in the form of support. So all these low density structure what you are seeing here are nothing but the support structures. To get the final shape, these support structures has to be removed by using the appropriate tool such as knife, chisels and all. Removing support material is a very difficult task, particularly in SLA. The worker has to be very careful because he should not damage the main material cured here while removing the support. Also, there is a big disadvantage here. As you can see, these support materials are already cured and cannot be reused. Hence, lot of waste is generated for large overhanging structures. However, the final product always looks good by this process, as you can see here now. This is because this is the most accurate additive manufacturing process as already mentioned. Now, in the case of 3D systems SLA, where a Zephyr is used, the only difference is the liquid material is not spreaded by deep dipping. Deep dipping means there is a part here which got cured, it goes down by a certain amount and then rise up to a certain amount, and then the new layer or the new liquid layer flows over it. That is the deep dipping. Instead, the recoating happens in this particular machine by spreading the layer of liquid material from top. So there is basically a hopper here. So assume that this is the hopper. This is the hopper, and there is a liquid material here inside. When it moves from this end to this end, the liquid material falls like a curtain and it spreads over the previous layer. That is why this type of feeding is called as top feeding. That is the only difference between 3D systems SLA, the conventional SLA, and 3D systems SLA which uses Zephyr. Now, what are the basic steps involved in stereolithography apparatus are highlighted on this slide. Of course, in the pre-processing, we first generate the support structures in the CAD model itself wherever it's required. You have already learned how to identify the region where support is required in an STL file. Then after that, a planar slicing operation is performed. This also you have already learned. It is nothing but taking the intersection between a horizontal plane and the group of triangles of the STL file. Then after the pre-processing, the build process starts. These are the steps involved in the build process. The first step is the table goes down by the required layer thickness and the new liquid layer is recoated. If it is 3D systems conventional SLA, then it is spreaded by a method called deep dipping, or if it is using the technology Zephyr, then the liquid resin will be spreaded by the top feeding. The beam scans the liquid layer for each loop. The border is first scanned basically. So for example, we want to make this particular layer in a slice. Then first of all, like we already discussed in our area filling lecture, first the outer boundaries are scanned and then the inside area is filled. So if 100% density is required, then definitely the step over will be, step over means the distance between the two consecutive passes will be defined based on that. Usually the outer contour is scanned with a smaller diameter laser. This is because it is going to give you the accuracy on the outer periphery, while the inside area is usually scanned with a larger diameter beam, and hence we can really save a lot of time in scanning these layers, because if we scan the inside layer with the smaller beam, it will take a lot of time, while if we scan the outer periphery by the larger diameter beam, then it may not be very accurate. Therefore, a good combination can be used to utilize in such a way that we save time as well as maintain the accuracy. After all the layers are made, the table of course rises completely like you have seen and reveals the part. Also, once the part is completed, of course, the liquid which is trapped into the uncured zone is drained out. So, for example, we are going to make this part, it will build like this. There will be liquid material trapped here. This can be drained out by just tilting the component upside down. Of course, there will be some zones, for example, some overhanging regions that the support has to be removed appropriately like you have seen in the video. This is the build process. Of course, after completion of the part fabrication, the post-processing starts. In this, the entire part is kept in a post-cure apparatus, where it is kept under UV light radiation to complete the photopolymerization. Usually, what we create on the bed itself is not completely cured, because we do not want to give much energy to the support also. As laser beam is required to scan these areas, it is an expensive process. While after completion of the part, if you keep the entire part into an apparatus, which is subjected to the UV light radiation, then it can complete the photopolymerization and make the part quite hard. Then of course, if required, the part can be painted and finished further. So this is the general process for building the part by stereolithography apparatus. There are several advantages and disadvantages associated with the process, of course. Advantages like, as this process uses galvanometers, those are consisted of tiny mirrors, can move the laser beam on the bed with a very high speed. The speed can go even up to 10 meters per second. Also, another most important benefit of the process is its accuracy. Like I have already mentioned, the process is the most accurate additive manufacturing process, because here you can spread the layer of the liquid with a very high accuracy. It may go even up to 5 micron or even less. Also, another benefit of this process is like you can make the pattern for creating the casting. 3D systems SLA, a particular name they give to create such pattern and call them as quick cast. These quick cast patterns can be further used to create the shell around, and then an evaporative casting process is used. There are few limitations, of course, for the process. It's a very expensive process because of the involvement of laser and the requirement of the liquid. This is another very important. As you have seen, even if you want to create a very small part, the entire tank has to be filled with the liquid resin. Otherwise, you will not be able to record the new layer. That is why, because of the involvement of lot of raw material also, the process is quite expensive. Also, the part which we produce by this process become brittle over the period of time because of continuing the polymerization through the ambient light also, because the UV light is available in the conventional white light also. Also, the parts are limited to only photopolymers. Like, we cannot use any random material for making the part by this process. The material has to be photopolymer. And of course, this process is not suitable for office environment as it is subjected to the fumes, and hence the health hazard issues are always associated with it. We have identified total 5 subsystems associated with the conventional SLA system. Those are, first, a UV laser. This is the laser beam which used as an energy source which scans the selected region over a layer of liquid photopolymer to cure it. As you can see here, written 1 here, this is the laser source. It gives you a sharp laser beam which passes through certain optics if required, and then got incident on a galvanometer. Based on the appropriate orientation of the galvanometer, the laser beam falls onto the liquid wet. Wherever the laser beam falls, that portion of the liquid will get cured. Now, if we are using a high power laser, of course, we will be able to cure it very faster and the depth of penetration may be good. But if the laser is not having a very high power, the depth of penetration and other process parameters will depend on that. Hence, it is very important to understand the curing process, that what happened when laser beam really strikes on the photopolymer bed. So, the power density of the laser spot and material properties are 2 major factors to govern the curing process. Hence, that process is shown here by 2. Then, the laser beam is positioned, like I said, using a pair of 2 mirrors, and that is called as galvanometer, which is capable of deflecting the beam in 2 directions. Being a very low inertia of these mirrors, the scanning speed is very high. So, this is another system or another subsystem which is subjected of our interest, and we will discuss it in detail. Then, in conventional SLA process, the entire part goes down like this, as you are seeing here, and the liquid material flows over it. As the liquid material flows over it, the layer which we just cured completely covered by the liquid. Then it rises up to a certain height, and then a recorder or a doctor blade wipes over it, and as it wipes here, it gives you the perfect layer height, as you are seeing here. So, this process is really very important because in 3D systems SLA, the scanning of layer doesn't take time, while spreading the new layer takes much more time than that. Hence, it is very important for us to discuss about this recoating system which was available earlier in 3D systems SLA. Then fifth is how we are moving this bed, because there could be different mechanisms for that. That is nothing but the Z axis of the machine. It could be having a rack and pinion arrangement like you are seeing here, or it can be a scissor lift mechanism. So some of these mechanisms we will see very briefly. So now our focus will be on these 5 subsystems. The first subsystem, like I have already mentioned, is the UV laser beam. So before proceeding further, now let us discuss a little bit about the principle of laser, so that you will be familiar with the terminologies which I will use not only in SLA but wherever in additive manufacturing processes the laser is used. Therefore, discussing the laser, the fundamentals of laser is very important at this point of time. So what is the laser beam? Laser stands for light amplification by stimulated emission of radiation. We all know that. So basically light is any electromagnetic radiation which act as a wave and particle. A particle with light energy is also called as photon. All types of electromagnetic radiation travels at the same speed in vacuum but vary in frequency and wavelength. Hence, different interaction with the different material. That is why we sometimes say that CO2 laser is good for ceramic and the solid state lasers are good for metals. This is because of having the different wavelength for these particular lasers, because different wavelengths give different interaction with different material. So this is how a typical electromagnetic radiation looks like. And the distance between the two peaks on the wave is of course called as wavelength. Depending on the wavelength, the electromagnetic radiation will interact with the material. This particular axis is showing the electric field of oscillation, this blue color one, and this pink color one is showing the magnetic field oscillation, and they both are perpendicular to each other. Laser used to have two very important properties. One is monochromatic. Lasers are monochromatic because the light which you see conventionally, the white light, is consisted of different colors or different wavelengths of light, while the laser consists of only a light of single wavelength, and that is why it is called as monochromatic light. There is a wide range of wavelengths available because it completely depends on the wavelength. So for example, if you say the green laser, this will fall in this range, will have the wavelength of range 500 nanometer to 600 nanometer. Like we are discussing about SLA, we have already seen it uses UV laser. Hence, it will lie in this range. This is the ultraviolet range from here to here. And these are the different types of laser or the active mediums, those can produce these particular lasers of wavelength for you. Another important property of a laser beam is the coherence. Means if you have seen an LED can also give you a monochromatic light. Means the color of the light could be same. Color means the wavelength of the light is same. As you can see here, this is a red LED. It is emitting the monochromatic light. The wavelength of the light is same, but the light which it is producing is not coherence. Meaning to say, the light is traveling with different phase at different location in different directions. While in a laser beam, as you can see here, this is a laser beam, and you zoom here, you will find that the light will be in coherence. Means it is in phase and in same direction. The light is traveling only, all the waves are traveling in the same direction and they are also in phase, in same phase. They are not having different phase at any location. If I take this location, the phase is this. If I take this location, the phase is this. So the laser is basically coherence in nature. So these two properties, monochromatic and coherence, makes the laser beam different from the conventional light. Now let us discuss about the principle of the laser. To produce a laser, there are 4 different phenomena occur. First is called as absorption. Second is called as spontaneous emission. Third is called as pumping, and population inversion, and the fourth one is stimulated emission of electromagnetic radiation. So let us discuss about these 4 phenomena. Assume that in an atom the electrons are having 2 states. This is state 1, that is also called as the ground state, that is basically the lower energy state of the electron, and there is another state which is called as the excited state. Now if there is a electron over here which is lying on the ground state of the energy, and a photon of light falls onto it, and it is having an energy h nu. If this energy h nu is equals to Ex minus Ez, which is equals to the difference between these 2 energy levels, then this electron will get excited and will reach to another state, that is the excited state. Hence the electron will be now here. Usually these electrons does not stay for a longer period of time here, and then immediately comes down. Usually they stay here up to for 10 to the power minus 8 second after absorbing the energy. So absorbing the energy and reaching to another level of the energy state is called as absorption. What happened after that? As the electron remains here for only very small amount of time, immediately its energy level falls down and the electron comes in the ground state again. While it comes down, it emits a photon back, which is of the same energy, h nu. This particular phenomena of emitting the photon is called as spontaneous emission. As this particular emission, as you can see, need not to be in correlation in phase, and hence it is not an coherence light. Means this photon which you are producing may not be in the coherence with the light which was incident on this. Also, if multiple photons are going up and then coming down, they will emit the photons at different times, and hence their phases may not be same. Means the light which we produce by the spontaneous emission may not be coherence. Now how to get coherence light? For that we need to discuss the 2 phenomena, that is pumping and population inversion and stimulated emission of electromagnetic radiation. So usually to produce laser we need to prepare an active medium. Active medium could be a mixture of multiple elements and hence have some unique properties. Those properties can be elaborated by this analogy here. Now I am assuming that there are 3 levels of energy, E1, E2 and E3. When a light falls onto the electrons available in the ground state or on the E1 level, energy will absorb the energy which is equals to maybe E3 minus E1, and hence the electron will jump into the high level of energy state, that is E3, and it will remain here only for 10 to the power minus 8 second as we already know that. But in this active medium, there is a unique property, and hence there is an intermediate energy state available, that is called as metastable state. So this was the ground state, this was the excited state, and in the active medium, like I said, there is a unique state available called as metastable state. What happens when the electron reaches here, as it stays only for 10 to the power minus 8 seconds, it immediately comes to the metastable state, which is an intermediate state, and here the electron usually stays for up to 3 into 10 to the power minus 3 millisecond, which is of course greater than this amount of time which is available for excited state. As the electron state stays in the metastable state for a longer period of time, it is possible that we can produce more electrons here in this particular state. So assume that if there are n1 electrons here in the ground state and n2 electrons are available in the metastable state, then if n2 is greater than n1, the phenomena is called as the population inversion. Usually we always have n1 greater than n2, that is the conventional, because more electrons will be in the ground state. To achieve this state of population inversion, you have to give sufficient amount of energy to the ground state electrons, and that process is called as pumping. So in the simple words, you can understand it like this: if I give certain amount of energy with a particular frequency and I pump more electrons quickly in the excited states, and they then come back and stays in the metastable states immediately, then in that case the amount of electrons available n2 will be greater than the amount of electron n1 in the ground state. So providing this sufficient energy is called nothing but pumping. So if we pump the active medium appropriately, we can achieve the population inversion. Now let us discuss about the last phenomena, that is stimulated emission of electromagnetic radiation, because our question still remains. What we want is to produce a light where all the waves are in coherence. So how can we do that? Now let us consider only E2 and E1. As I have already said, there are a lot of electrons here in the E2 because population inversion already occurred, and there are few electrons here in E1 also. So now what will happen when a photon of energy h nu, which is equals to E2 minus E1, incident from an external source on the active medium or active system, the light energy in the form of photon stimulate elements in the state n2 to undergo transition to the state n1. So this particular electron, for example, is going down, it will be here and it will emit an photon of h nu energy. Now this particular photon will not emitted on its own, while the energy provided from the external source to the active medium will stimulate this photon from the electron, and hence now both of these, the photon which is coming from the external source and the photon which is emitted by the electron, are in the same phase. Hence the light which we are producing now, or these two waves, if you see these two photons, they are in the same phase difference. That means they have the same phase at any location. Now the light is coherence. When this stimulated emission dominates the spontaneous emission, we can successfully generate the laser. So this is how the laser cavity looks like. So this is the cavity of a laser, typical laser. This is the fully reflective rear mirror, means when the light will strike from here, it will reflect back completely. While this is the output coupler, which is also called as partially reflective front mirror. When a threshold occurs, the light will even pass through this. Before that, it will definitely reflect back. So here you can see you are pumping it from the outside and there are photons available inside. As we are pumping from outside, the atoms available in the ground state will get excited and reach to the excited state atom. When the atom will reach to excited state and you are appropriately pumping from outside, the population inversion will occur. Hence, there will be more atoms available in the excited state than the atoms available in the ground state. Now, if we give sufficient energy from outside, which is equal to the difference between the two state of the energy, that will emit electron or stimulate the photon from the excited atom, and hence the energy will be released in the same phase. So this is how basically the laser works. Now let us discuss a little bit about the two types of modes in the laser. As this is the mirror 1, this is mirror 2, the light can form different modes of the modes inside the cavity. And of course, this particular one is called as the longitudinal mode, and if I cut the beam from its cross section, and what we are seeing there is called as transverse mode. Essentially, they both are independent to each other. The transverse dimension in the resonator is normally considerably small than the longitudinal one. So what happened? Let us first discuss about the longitudinal mode. So if, for example, this is the wavelength of the light we are producing, and that is represented by lambda, and the mode is n, means there are n ups and downs in the cavity. Hence, we will definitely say that n lambda will be equals to L. So as length of the cavity is constant, either we can have different mode or the different values of wavelength. In this case, you can see as the mode increases, definitely the wavelength will decrease for a particular length of the cavity. However, we will see that we will not be having much difference in the wavelength if the mode changes by a little bit. However, if there is an aperture here, for example, from where the laser light is going to go out, that aperture may not be having everywhere continuous light. It may be having somewhere or may not be having at some places, and that is because of the interface. The number of the illumination on the aperture side or on the cross section of the laser beam are governed. The number of fully illumination on the transverse beam usually defined its quality. Also, it is called as transverse electromagnetic modes. It basically describes the shape of energy distribution in the energy beam cross section. So for example, this is TEM00, meaning transverse electromagnetic mode 00. Here you can see in this black zone, it's a fully bright area. While if you see in TEM01, there is one zone which is not fully illuminating, means this is a dark area here. There are two spots where we are getting fully illuminating area. Now this is TEM31 and this is a combination of TEM10 and 01. So how we defined it basically? So this 1 is given corresponding to the number of not fully bright or not fully illuminating spots in the x-axis. So if this is the x-axis and this is the y-axis, as you can see here in the x-axis, I have one spot here, this region, one spot only, that is not fully illuminating. That means I am writing one spot available along the x-axis and there is no such spot available along the y-axis. As you can see on y-axis there is nothing. Hence it is TEM01. Here it is TEM31, meaning to say there will be 3 not fully illuminating spots available in the x-axis. So this is the x-axis, let us count, this is 1, this is 2 and this is 3. So yes, there are 3 such spots available along the x-axis, while along the y-axis only one such spot is available, that is here. Hence it is written as TEM31. Then there is a combination of course here TEM01 plus TEM01. So meaning to say it is a combination of this particular one, which is TEM10, and if I draw the TEM01, that will look something like this. Something like this. So a combination of this one and this one will look nothing but something like this, right? It will have a center spot where there will be no illumination. Hence, it will look something like a donut laser. So this is how we defined the cross section of the laser beam, and it is very, very important for our further discussions. And the most preferable in the SLA is TEM00. This is because it doesn't have any spot where there is no illumination. We will discuss these topics in the upcoming lecture. Thank you very much.